So, well, then the next speaker is Ruben Hidalgo from Universidad de la Frontera in Temuco, Chile. And he will talk of a really intriguing title, the Loch, Ness, Monster, and Homology cover. So you have 40 minutes, Hidalgo, and thank you very much.
Thank you, Carlos. Thank you, the organizers, for inviting me to give this talk. Okay, first of all, I want to apologize because probably this talk is kind of a little far from Buddhism talks before. So yes, I want to talk about a joint work with Adam Smejan from QE. And this has to do essentially with coverings of Riemann surfaces, and in particular about the homology covers. So just let me see if this is. So first of all, I want to show you a photo of maybe the Loch Ness monster that you know. So my talk is not about him, so it's something else. So okay, so in this talk, all the surfaces I will talk will be connected, how orientable, second countable, right? In this case, the surface has two possibilities to be of finite type. So the fundamental group is finite generated or is infinite type otherwise. Yeah. So classically, we have the classification of finite type Riemann surfaces. So essentially, they say, I will show you the picture for it. So essentially, all these finite type surfaces are obtained by a compact surface, some genus G, by deleting some finite number of points, some endpoints. And this is a picture of genus 2 with three points deleted. So this is the type GM, and this pair classifies topologically those finite type surfaces. So there is equivalent classification for infinite type surfaces due to Karajatov and Richards. We say that essentially we have a tuple which classifies topologically all these infinite type surfaces, which is given by a genus which can be infinite, so it can be infinite genus surfaces or finite genus. And there is a couple of netted set, closed set in the counter set, which are called the ends. I will not go into details about this. I will show you a picture. So essentially, we have some place where to go in the infinity, and some of these places are non-planar. So let me show you some examples. So essentially, you start constructing the Cantor set. So here, typically how you start by deleting cells of the intervals. Then you can, above this, to make a construction by these Legos, either pans or a genus 1 pans, okay, by gluing together in following this picture. You are allowed to stop at some moment. Here, for example, and you just close and or continue. So all these surfaces, which are infinite type, are constructed in that way. Yeah, so this is it. So here is the simplest one of infinite type, which has infinite genus, has exactly one end, this one over here. And this infinite end is accumulated by genus. So this has exactly one end, which is the same infinite genus. So this is called the Loch Ness monster in our talk, okay? There are many other surfaces like flute or Bloomberg tree, Cantor's surfaces, but this is the one. Oh my God. Okay, sorry. This is in Spanish. All these surfaces, infinite type or finite type, carry the structure Riemann surfaces. So you can provide Riemann surface structure to these surfaces or not, and the families of surfaces that a particular surface has could be infinite dimensional in case of infinite type, or in the case of finite type, you have finite dimensional structure. This is model space of taking spaces. Essentially, you can move with the Riemann surface on these surfaces. Yeah, so let me go to to Kleinian groups. So just recalling some stuff, you have the Riemann sphere, and then you look for the conformal automorphism Riemann sphere. These are the Möbius transformations. So this object, rational map of degree 1. And let me call M or PSL2C this group of Möbius transformation. So what is Kleinian group? So we're going to talk about discrete groups of Möbius transformations. Okay, so this is for us a Kleinian group. Nowadays, these Kleinian groups always can say that they are first kind or second kind, depending on if they act discontinuously or not somewhere in the Riemann sphere. So let me go to this. So a discrete group of Möbius transformations produce a dynamical system on the Riemann sphere. And such dynamical system essentially divide the sphere into portions. One portion is where this dynamic is normal, and the complement where this dynamic is chaotic. So, for example, where is this dynamic is normal is the points where the group acts discontinuously, properly discontinuously in this case. So essentially, these are the points. This set can be empty, but essentially the points with finite stabilizer by the group, and also containing a neighborhood which is moved away by all of the elements of the group, with exception of a few of them. So essentially the one that keep invariant the point. This is called the Riemann discontinuity, or the Fatou set if you are in the world of complex dynamic. And the complement, where the chaotic situation happening in dynamics, is called the limit set of the Kleinian group. And the cardinality of the limit set is either zeros or it's maybe empty. So it's case of when the group is finite, 1 point, 2 points, or infinite number of points. When there are infinite number of points, we say that the Kleinian group is a non-elementary, and when it's finite number of points, is elementary groups. In this talk, I will talk about non-elementary Kleinian groups with non-empty regional discontinuity. Okay. So far, there is questions. Okay. So, interesting second kind of Kleinian groups we call function groups. So, what is this function group? It's a pair where you see a Kleinian group in here. Will be finally generated Kleinian group with non-empty regional discontinuity. And delta, here the second component, is a component, it's connected component of the regional discontinuity, which is invariant under the action of the group. Okay, so these are the pairs which are interested now. When you have one of these pairs, and the action of this component delta is free, so no fixed point, then you have the quotient will be a Riemann surface. But Alford-Fenix theorem says that this surface is of finite type, in particular gamma, because gamma is finite generated. So will be something like this. Yeah, so it can be with some punctures or not, but has finite genus. The condition for gamma to be non-elementary is essential to say the Euler characteristic is negative, or written in this way, this number 2g minus 2 minus n plus n is positive. So in this case, like this. So let me talk about commutative rigidity, of also can be called the Torelli theorem at the level of Kleinian groups. So essentially, if you start with two torsion-free non-elementary function groups, so you are in the presence of two surfaces of finite type, then you can consider the commutator subgroup of each of these groups. They could be different or equal, and the commutator rigidity say that if the commutator subgroup are equal, then the function group, the Kleinian groups, are equals. This result started by Bernard Maskit in 1986, where he considered the case of the component to be simply connected, for example, the unit disk or hyperbolic head plane. And the quotient is compact Riemann surface, so no punctures. And he, at that time, was trying to find some Kleinian groups argument to prove Torelli theorem, classical Torelli theorem. Then in 93, it was able to delete the condition of the compact, so we may have punctures. And finally, in 95, it was proved the general situation. Okay, so essentially here, in this case, let me see, in this case, to provide an idea, is that you have your surface. So you have two objects in here. You have of course, the homology of the surface with integer coefficients, and you have the holomorphic forms on the surface. This is a G, if this is genus G, this is a G complex G-dimensional vector space. Then you have the dual space, this one forms by integration of curves, by integration of forms on curves, produce an embedding in here of the homology as a lattice. So you have a torus. Such a torus is called the Jacobian of the surface. The intersection forms on the homology induce an alternating form on this space, and in particular introduce an emission product. And this is a principal polarization on the torus. So this is a particular case of principal polarization Orion variety. And so to S, you can associate this Jacobian. And Torelli theorem say that if the Jacobians are isomorphic as principally polarized abelian varieties, then the surfaces are also isomorphic. So this part you can see as the Kleinian group context of this algebraic setting. Yeah. So the question would be that now, since we have this general situation, should be some kind of Torelli theorem at the level of non-compact finite type Riemann surfaces. So what is this Torelli theorem? Yeah, so this is essentially an idea. So the question is, okay, we have this function group, take the commutator group, and look at this Riemann surface. So the question is, how it looks like this Riemann surface? So this is kind of the Torelli surface associated to the uniformization. So you have delta over gamma. This is a finite type surface. And you want to tell about which kind of surface is this infinite type surface. Yeah. So this is the commutator group is field generator, so it is infinite type surface. Which one it is? There are uncountably many of these infinite type surfaces. Which one it is? Okay. So we have this. We have our torsion-free non-elementary function group. We have this represented Riemann surface. So have some genus G, some number of punctures n. Non-elementary, we say that was meaning 2G minus 2 plus n is positive. And that means essentially that we are taking care of some only possibility. For example, if no punctures, means the genus had to be at least 2. If we have either 1 or 2 punctures, the genus had to be at least 1. And if G is 0, at least 3 punctures in this case. So let me take care of the case n equal 1. So a surface with only 1 puncture. Why you can say this? So here is what did we see? If you take a small loop around the puncture, this small loop is homologically trivial. So what that means, that when you lift this to the homology cover, this loop will lift to loop, and this part will lift to a puncture. So the surface that we are looking for, in the case n equal 1, will have punctures, okay? If you have more than one puncture, if you have two punctures, then no punctures will be surrounded by an homology loop. So this will not produce punctures in your homology cover, okay? So this is the only case where punctures in downstairs can produce punctures in the homology cover. So n equal 1 is a problem. So let me give you an example, a puncture tori. So each puncture tori can be uniformized by a free group of rank 2 given by generators, which looks like this. Two hyperbolic elements, yeah? So we can say that this is minus 0, 1, and sub lambda bigger than 0, 1. And we produce this. So when you look at the commutator subgroup, you see this picture. You quotient the commutator, you have the plane, the complex plane, minus a lattice. This lattice is generated by some complex number with imaginary part positive. And what is tau is exactly the tau that provides uniformization of the compact genus 1 Riemann surface after you added the puncture in here. So this is the situation. So here, for the case of puncture tori, the homology cover is the complex plane minus a lattice. And the lattice corresponds to the Riemann surface structure of the closed surface, which is obtained by adding the puncture. So it's the elliptic wall. Okay, so a resulting paper with Catariguana Garcia, Quispe, and Ramirez Maluenda, we obtained this simple fact that if you start with a compact Riemann surface, so no punctures of genus at least 2, so no elementary. So this surface is, we say that is given by the H2 divided by this group, this compact torsion-free subgroup of rank 2, of genus 2. So if you take any characteristic subgroup of infinite index, then the quotient, the uniformizing surface by this characteristic subgroup is topologically the Loch Ness monster. So in case there are no punctures. In particular, characteristic subgroups of infinite index for gamma, for this gamma will be the commutator subgroup. So the first consequence is that for compact Riemann surface of genus at least 2, the homology cover is topologically the Loch Ness monster. Another characteristic subgroup is the commutator subgroup of the commutator subgroup of the gamma. So in this case, since the commutator subgroup provide the Loch Ness monster, then the homology cover of the Loch Ness monster is again the Loch Ness monster. So essentially we have this situation so far. So the question is, well, how frequently is that the Loch Ness monster is the topological type of these commutators surfaces? So with ARA, we prove the following result. Let's start with the torsion-free elementary function group of type Gn, and then we obtain that this surface, which is the uniformizing by the commutator subgroup of the function group gamma, is topologically the Loch Ness monster, except in the example we showed before, except when we have exactly one puncture, because this one puncture will produce punctures in this object. So except by this situation, we have the Loch Ness monster. So we have this picture. In particular, if you take a surface of genus G with one puncture, and you do the same, then this surface will be again the Loch Ness monster, except that we have to delete the orbit of the puncture by the group, by the homology group, by gamma over gamma prime. So this is the orbit of puncture by the homology of the uniformizing in here. So this is the picture, more or less. So these punctures are called finite ends, and this is the infinite ends. So for example, one could start talking about maybe cover this of Loch Ness monster, for example. Instead to start with the compact surfaces of genus G and look group of automorphism on this surface and try to find extension to a manifold where the surface is boundary. You can say, okay, I will take the Loch Ness monster. So let me go to this one and look at a group acting on this surface. Try to extend to a three manifold, which will have one end, and whose boundary is this surface. So this, you can think of this about the infinite genus handle body, with the boundary, the infinite genus surface. So in the case of finite type, so when you have a finite group acting on a compact Riemann surface, the condition for extendability is equivalent to find a collection of simple loops, which is invariant under the action of the group, and cut the surface into genus C, into planar surfaces. So in here, is this also true or not? We have more groups, and the infinite order groups in here in play. So more or less the idea of the proof is very simple. Let me just talk about the case of simply connected component for simplicity. So what we have in here, we have then our delta. We have the group acting, and we have a finite type surface in here. And we want to discover what is this, right? In here. So in here you have the action of gamma over gamma prime, which is some a finite number of copy of the integers, and this n in each case is given by 2g if n equals 0, so no punctures, so the homology, or is the homology of the surface with punctures, which is this number. In any case, the condition of to be hyperbolic in here is equivalent to say that this number n, this power in here, is at least 2. So what happened? When you look at this group and you look at the space of n of the group, so you look at the, here's the finite generator, so no problem. So in this finite generator, you can take the Kelly graph of this group for a given finite set of generators. And in this Kelly group, you can look at the ends. For this case, when n is bigger or equal than 2, then we have one end. In the case of set, we have two ends. Yeah, so we are not in this situation. Okay. Also, we know that this is an infinite type surface because gamma prime, the commutators will be infinitely generated. We have seen that this quotient has no punctures because n is different from 1. The only case we produce punctures when n equals 1. So we do the following. We take a canonical set of generators for the fundamental group of the surface, like this, the red, blue, and green curves. So we have a presentation, canonical presentation. And we do the following: we lift these loops to the homology cover, and when we lift this, we obtain a copy of the calligraph of our group, our abelian group, in terms of these generators. As before, this was our CM with n equal than 2, so which has one end, has no isolated ends, had infinite genus, so it's an infinite type surface with exactly one end, so it is the Loch monster. So this provides an argument. In the case of when delta is not simply connected, one has to take care of some detail, but the idea of the proof is more or less the same. Okay, so essentially, this happened with the finite type surfaces, and providing a variation of this argument, we are able to prove also that the homology cover of every infinite type surface is also topologically Loch monster. Essentially, Loch monster is predominant in this collection of infinite type surface at the level of commutators liftings. So probably what is one can study now is about the Miller space of Riemann surface extraction of the Loch monster. There's a lot information about the Miller space of infinite type surfaces or the Miller spaces of infinitely generated function groups. So essentially, this can be studied, and there are a lot to recover information from there. And also, this provide a tachymeter space which in some way contains the tachymeter spaces of finite or compact Riemann surfaces. So you have some kind of subset, submanifolds on these tachymeter spaces. And one would like to see if they belong to the same connected component of tachymeter space of Loch monster, or they must belong to different connected components. Yeah. Essentially, this is what I want to talk, and I think it is also, I give you a lot of time. So this is all.
Thank you very much, Ruben. Is there questions? I was thinking, do you know this is the fundamental domain that occurs in the hyperbolic plane, that you have the signature is 2, 3, infinity. So I don't know, but well, you put the Loch monster as something that is like some place where when you arrive and you quotient by the commutator group, so you are under some conditions. So there's not some reasons or some relation with that, that there are some universal properties that say that.
I don't know if I follow your question, but essentially you're asking if how this homology covers, right? About the some universal property of homology cover. So essentially, look, what I say in the beginning, that the homology cover permit to separate different Riemann surfaces. Mm-hmm. So, okay, one will say, okay, why to go to infinite type surface in order to give information about finite type surfaces? But this infinite type surface carry all this information, what I call it, about this Torelli theorem. So it's one would like to give a Riemann surface Euclidean group proof of this Torelli theorem. That is one of the reasons why I will be interested in this London monster. But also there is, in the last year, have been a lot of people working on big mapping class groups. So London monster is one of these nice infinite type surfaces where many properties that are in some sense valid for a mapping class group of compact surface or finite type surface are somehow valid in the London monster. Okay, not all of them. There are many other problems. In other infinite type surfaces, it's more chaotic the situation than. But this is probably a way to try to study information about the big mapping class group of the London monster and relate it with the surfaces. You see, we have a lot of different type of surfaces, compact surfaces of genus 2, 3, 4, 5, surfaces of genus 2 with 5 punctures, all of them producing the same London monster by the homology cover. So is this information enough to codify in some way the mapping class group of the London monster, for example? So in going the other direction, from finite to the infinite type.
And well, I just have another question. Is there not here the long monster is something that has infinity genus and has only one end? So yes. And well, Rita, maybe it could be interested. So there are some stabilization of the homology of the mapping class group, yeah, in terms of that. But maybe there is another long monster that has infinity punctures and not genus.
Okay, there are, you see, I told you in this result of Creato means you take any closed set of the Cantor set, and you can construct an infinite type surface with such a collection of infinite parts. And even you can construct to, let me try to go back to, you see, you start with any couple of closed subset of the Cantor set in here, and any genus, you will construct a surface with these invariants, which will be unique up to topology. So you can construct a lot of infinite type surfaces. There are surfaces, infinite type surfaces, which, for example, has a non-depressible surface inside, like this, for example. And here you have infinite type surface with 3 ends. Each one of them is non-planar, so here is equal, and there are only 3. And in here, each time that you have an homeomorphism of the surface, you cannot, essentially you take any DTs and you take the image of this will always intersect this one. So non-displacable surface. So these surfaces, for example, with this property, which is not the case of the London monster, produce a lot of problems when studying the big mapping class group. For example, in the London monster, just to say something, okay, let me see. If you give me any countable group, I can provide, this is Patel, Blamis, and Nick Blamis, Nicholas Blamis, Patel, and someone else, I don't remember, that say that you can give a Riemann surface structure to the London monster such that this group that you give me is the total group of isometries, okay? But for this kind of surfaces, the only group that can appear as a group of isometries are finite. So it's clearly different type of infinite type surface provide different type of situations or different words depending on the type. Learning monster is quite nice. It's like to be working with the close Riemann surface in somehow. So you can think about handle body, right? Infinite type, high infinite genus handle body, whose boundary is the learning monster. Has sense, right? So you can tell about extendability of group of automorphism of the learning monster to the interior of its of this infinite handle body.
But that this has some implications in, for example, in the morpheme conjecture, stabilization problems. No,
I don't know. I don't know.
Is there any other question? Well, I think there's no question. So thank you very much, Ruben. Yeah.
No, thank you to you.
Really intriguing subject and nice.